Interesting polynomial behavior. So we're going to graph a quartic function. Cubic function is biggest power of x is going to be x cubed. And does everybody see that if I were to, this is quartic, right? That's a polynomial with one term. What do you suppose we call a polynomial with one term? Quartic. How do you say it? Poly means many. How do you say one? Mono. Yeah, it's a monomial. Okay. How would you say a polynomial with two terms? Binomial. Yeah. How would you say a polynomial with three terms? Trinomial. And we don't always say that stuff. Like we would just call these. This falls under the umbrella of a polynomial. It is a polynomial. It just happens to have one term, right? What about this guy right here? X cubed times x minus 2. Do you see that that's not written in polynomial form, right? Remember what polynomial form was from yesterday. Polynomial form, actually I can just go right to it. It's that, right? Take a picture. So this is the generic way we write a polynomial. So just, to summarize what this is, it's just a sum of terms, right? And each term has a real number coefficient and a whole number exponent, right? Okay, so we're going to look at a bunch of these. This is our topic we're going to be discussing here for next week or so. Do you see that if I were to expand this out, in this case, if I distributed the x cubed, I would end up with a polynomial in standard form. Right now, this is in what we call factored form, right? Which is really useful. That's oftentimes when we're doing stuff with polynomials, like in calculus, we do a ton of stuff with polynomials, and we're always trying to get things into factored form because factored form allows us to find zeros of functions, and that's usually what we want to do. Same thing here, though. Do you see that if I were to expand this whole thing out, I'm going to get a whole jumble of terms, but what's the leading term going to be? What's the most powerful? What's the biggest exponent I'm going to get for x? If I were to multiply x squared times x minus 2 times x plus 2. X to the fourth, right? And you can kind of see, if I were to do something like that, like let's just say we had, let's even take one like this. What if we had x times x minus 2 times x plus 2 times x plus 3. That's a long process of expanding that whole thing out, right? I'd have to do this, we'd multiply things in pairs. So I'd have to first distribute the x, let's say, right? And then get something. Well, I'm going to get something when I do that. Would you agree, like x squared and then some other terms? I don't even care, right? We just want to focus on what the biggest term is going to be. When I multiply this times x plus 2, what's the first term going to be? The x cubed. When I distribute the x squared, I'm going to get x cubed plus a bunch of other stuff, which I don't care about. Lesser powers of x, right? For this purpose, I don't care about. Then if I bring down the x plus 3, and once again, expand out by distributing, what's my leading term going to be? It's going to be 1x to the fourth, isn't it? So I'm going to end up with x to the fourth plus a bunch of other stuff, right? So this is going to be a quartic polynomial, quartic function, because it's going to have x to the fourth is going to be the biggest power of x, right? Agreed? Okay. If I were to want to talk about, let's say, just quick review of yesterday. If I wanted to talk about the end behavior of this function then, right? What's the only term that really matters? Remember we did that thing yesterday where we looked at that function, and as we panned out, it started to gradually assume the behaviors of the more powerful terms, the bigger exponents, right? They were kind of suppressed by the real tiny coefficients, but eventually, which term dominated when we panned out a ways? X to the fourth, yeah, the leading term, right? The biggest, the first term when we write it in standard form, the biggest power of X is always going to dominate the function at the tails, right? And so if we're looking at the end behavior, really the only term we care about is that first term, right? What if we had, let's just say this had been a negative 2x plus 2 in that factor? What would have happened in the end when all the dust settled? What would the first term have been? Negative 2x to the fourth, because to find the leading term of the polynomial, what did we end up doing? We really just multiplied the leading term of each of those little factors together, right? To get the leading term of what the final polynomial in standard form would be, right? So if we're looking at end behavior, we don't care about the rest anyway. All we would have cared about is that first term, right? So let's take this one then. Let's look at the behavior at the tails. As x approaches positive infinity, f of x, and let's just call this whole thing f of x. F of x approaches what? And just don't say anything yet. Just want to think about that for a second. You should have your notebooks out, everybody. What do you think? Kristen, what are we going to get?
Positive infinity?
What's your thinking?
Multiply by an even square root, or root, whatever.
Okay.
It's always positive.
Right. What about that negative 2, though?
Okay, I think negative.
Negative, wouldn't it? Yeah, because I'm going to end up with a negative. I'm going to have two factors there. I've got my negative, which is the constant, times x to the fourth, which would be positive always because it's an even exponent. Very good. So we get negative infinity. What are we going to get as x approaches negative infinity? F of x would approach what? Negative infinity again. Good. Okay, and that tells us a lot. That tells us everything the function's doing way out there and way out there, right? At the tails of the function. Okay, so point I'm making is, even though this is written in factored form, we know two things about it, important things. If we expand it out, the biggest power of x is going to be x to the fourth, and more than that, the leading term is just going to be the product of x and negative 2x and x. And so that allows us to get the end behavior, right? Okay, now let's step back and let's look at some other stuff. We want to look at the behavior closer to home, not just the end behavior, but the behavior, like closer to the origin, see what's going on. Because this is where all the action is happening with this polynomial. Everybody agrees, though, that if I were to expand all these out, in each case, I'm going to get a quartic polynomial, right? The leading term is going to be x to the fourth. Everybody agrees? So everybody sees that? Okay, so let's see what we get. Let's look at x to the fourth, and this is the handout that I gave you. Does everybody have the handout? Where did I put? If you came in, everybody got one? Anybody walk in late and not get one? No, these aren't the ones. Oh, right here. If you need one, there it is. All right, so x to the fourth. Let's try this one out. You know what this looks like. What's it going to look like, x to the fourth? Somebody describe. When I type in x to the fourth, what's going to show up? Okay, it's kind of a parabola, but it's a little bit more squared off, right? It looks very similar to a parabola, though. So there it is. So let's answer the questions then, and just fill in that first column on the handout. So how many distinct factors are there? One, right? Does that make sense? There's one distinct factor. What are the x-intercepts? 0, 0, right? Okay. Now this is kind of important here, so let's just fill this first column out. Be filling this out and hang on to this thing. And when you look at that x-intercept, is it tangent to the x-axis or does it cross the x-axis? Okay, and what does the word tangent mean? Okay, so it's just going to graze it, right? A good way to think about it is, and Desmos helps me with this, if I focus in really, really close to the point, to the x-intercept at 0, 0, the function is going to look linear, and it's going to look just like the x-axis, right? So if I do, we can actually see that happen. Right, you can see that happen there. There's my function. It looks pretty linear, doesn't it? Right, that's a good visual demonstration of what it means to be tangent to something, right? Okay, but we'll come back out here. Okay, so then we've got tangent to the x-intercept. How many turning points? What's a turning point? Okay, where it turns vertically, right? So how many turning points are there here? One. Okay, so turning points could be defined, like if we were to think about this in terms of a topology. And a lot of times in math, it's good to talk about things topologically. In calculus, we do this a lot. We talk about the characteristics of a function. We look for extrema, which are minima and maxima. And then we look for some other topological features too. But what's a minimum? Okay, where it's the lowest point, it doesn't necessarily have to be the lowest point everywhere, but it's going to be the lowest point locally. And so topologically, what does a local or a relative minimum look like? How would you describe that if that was like a geological feature? What would you call that? That kind of a thing. Yeah, a valley. Yeah. So a minimum is really just a valley, right? And in calculus, kind of looking ahead, I like to get you thinking about, just anticipating what's coming up in calculus. We'll talk about the characteristics for why a function would have like a rounded valley like this one, or it could be a sharp jagged valley. And that's important stuff in calculus. What about if I were to flip this around so it became a maximum? I'm not going to do it. You can just use your imagination. What topologically does that look like? Yeah, a hill or a peak. A lot of times we call it a peak, right? And so turning points are really always going to be either peaks or valleys, right? So in this case, we have one turning point. How many global maximum values are there? None, right? There is no highest point on this function, is there? A global means everywhere, right? We talk about something that's a global issue. It's an issue that affects everybody on Earth, right? So I mean, it's everywhere. Local or relative is something that's maybe just more something that's happening in our area, right? So there is no place an ant could go on this function and say, proclaim, I'm at the highest place on this function, because it goes up forever, right? How many global minimum values are there? There's one global minimum right there, right? Does that make sense? And that's also a relative, they call them locals in Europe. Yeah, that's also a local minimum, right? But it just so happens that if there's only one local minimum, and that's the only turning point, then it's also global, right? You see that? In order for that to not be global, this function would have to turn again and plunge down, wouldn't it? You'd have to have at least two. You see that? Okay? So there's our exploration of x to the fourth. Now let's look at the next one. Okay, the next one is x cubed times x minus 2. Okay, that's a little different. Okay, so let's fill out this column. We're going to see if we can see some patterns here. How many distinct factors are there in this function? 2. We've got the x cubed, right? So x is a distinct factor and it's being cubed, and x minus 2 is another distinct factor, right? There are 2 of them when I factor it. Where are the x-intercepts? 0 and 2. And that makes sense to us, doesn't it? Because we've spent some time at the beginning of the year reviewing and talking about the zero product property, right? And so if I take the function f of x equals x cubed times x minus 2, and I want to find the solutions of that equation, right? by the zero product property, the solutions are going to be when the function equals 0, right? When y equals 0, that's going to be either when the first factor is 0 or the second factor is 0. And so that ought to be very consistent with the discussions we've had in the past. So either we're going to get x equals 0 or x equals 2, and that's what we see, right? So that part should make sense. What about the third row? Tangent to or cross the x-axis at the x-intercepts. Okay, it does both, doesn't it? It does both. And this and put this in your notes. Notice that it's tangent to the x-axis at 0. Would you agree that if I were to zoom in right there really, really close, the function would look linear? Okay? But at 2, it clearly just crosses through the x-axis, doesn't it? Okay, so get both of those in your notes because we're gonna see a pattern developing. How many global maximum values? None. How many local maximum? Is there a local maximum here? There isn't. This one's trying to almost be a maximum, but it's not, is it? Yes. Turning points. We missed that. Yeah. Okay, you tell me, how many turning points are there?
1.
Okay, is it 1 or 2? That's good. It's a good debate here. There is a definite answer, but what do you think? Somebody who wants to argue this, and this is healthy, even if argue for 2. Can't do it. It's hard to do if you think it's 1. Okay, argue for 1.
It never starts going up until it gets over.
Okay.
Y.
Good. This technically is not a valley, right? It's not a valley because it doesn't turn up on the other side. Think about it this way. What would happen in a valley? In a valley, if I were to roll a ball down, place a ball any place on the slope of a valley, what's it going to do? It's going to roll down, isn't it? Right? So in order for there to be a turning point, there would have to be, and for it to be a valley, there would have to be a place. Each turning point would have to include a place where I could set the ball and it wouldn't roll. There's no place here where I could do that, is there? You might think you could do it there, right? But if the ball has any size at all, and let's assume there's no friction, then it wouldn't work. It wouldn't work. It's gonna roll, right? Because if I zoom in on this, I'll see that there's only one point there that has 0 slope. One single point, and one point has no size, right? That make sense? Okay. So because it never turns back up, that's actually not what we call that. You'll learn this in calculus. That's called an inflection point. It's not a minimum. Okay. This clearly is, isn't it? So we get one relative minimum that is also a global minimum. Okay. And so I guess we just answered our question. To the next one. We have one relative minimum that's a global minimum and no relative maxima, right? Certainly no global maximum. Okay? Questions on that? Let's move on. Next one. What do we got? Okay. So yeah, kind of a W. Okay, what about this guy? How many distinct factors? 3, okay. What are the x-intercepts? -2, 0, and 0, okay. Tangent to or crossing? Both. Where is it tangent?
0.
Okay, it's tangent to at 0, 0 again. And it crosses at x equals -2 and x equals +2, right? Everybody agree? Okay. How many turning points? 3. Okay. Good. All right. Are there any global maximum values?
Yes.
So there. Remember what that says. How come no? It's local. Good. Because the ant couldn't say he's at the highest place because an ant could stand up there and be higher, right? But locally speaking, he's on a peak, so it is a local maximum. One local maximum at 0. Are there any? How about local and/or global minima? Two of them. And they're shared, aren't they? They're both local minima, and each is also a global minimum, right? Because it's a tie, if that makes sense.
What would it be if it was, could you have like two global and zero local? Or would it have to be?
We could have, in a function, we could have like one global, and then what if I tweak the function so this one didn't go as low? So then we could have both. Okay. All right, make sense? Okay. Last one. Oops, I did, didn't I? There we go. Okay, that's getting a little complicated. Why don't is there a way I can turn those off? Oh, yeah, that's good. Okay, perfect. There we go. So if I zoom out a little bit there. What do we got this time? Weird looking function. Okay, so what do you think? How many distinct factors are there this time? Here's the function. How many distinct factors? Four. That times that times that times that. We're really just asking how many things are being multiplied together, right? Four things. What are the x-intercepts? -3, -2, 2, and 0. Makes sense, right? That's what we would have said, a month and a half ago, right? Are they tangent to or crossing? They all cross this time, right? Every one of them crosses. None of them are tangent to, okay? How many turning points? 3, right? 1, 2, 3, okay? And how many, let's discuss the maxima. There's one local maximum, and how many local minima? There are 2, and one of them is global, right? Okay. So let's see if we can. Well, I'll tell you what. Let's do one other thing. Let's do one other thing. I didn't give you this sheet, but here, I'm going to copy it real quick. Okay, I hate to stop you because I could just hear good stuff going on, but let's kind of bring it all together, and I think we got a pretty good start for our thinking on this. So let's fill in this first column, and you guys raise your hands and help me fill this out. How many distinct factors does this first one have? One. Okay. What are the x-intercepts? X equals 0, and that's it, right? Tangent or both?
Cross.
How come tangent? It is tangent.
Because if you zoom in on it, it looks linear.
Okay, it's going to, but I kind of want to know now, why is that? Like if we go back to your chart for a second with the quartic function. I want you to look here at look at row 3 all the way across. I bet you're going to find when you look back at that the first 3 columns, although some of them may have some places where the graph crosses the x-axis, all 3 of those are going to have a tangent also. And where's it going to be? At 0. But it disappears here. What's going on? It moves from the origin, right? How come, what about these first 3 columns produced a tangent instead of a crossing pattern for the x-intercept? Okay, yeah, look, here it is. Look at this. In each of the first 3 columns, one of the factors, and in this case it's the factor x, is a multiple, right? It's taken to a power greater than 1, right? It's a multiple root, we could say. And so whenever that happens, that seems to give us, doesn't seem to, it does give us that tangent behavior. And so in each of these ones, you had in your notes, you should have, that it's tangent to the x-axis at x equals 0 because of that behavior, right? Okay, so now if we scoot up to this table then, let me ask you again. Tangent or crossing? Tangent, right? It's going to be tangent. How many turning points? None. None, because it's only got one. Does that make sense? Only got one x-intercept. And we know what the end behavior is going to be for a cubic function, don't we? So none. And then global minima and maxima? Relative? None. That sketch, we know what that one looks like. It just does that, doesn't it? Right? And there's that, I didn't draw it very well, but there's that tangent where it crosses the x-axis in the middle, right? Okay, so moving on. Let's try the next column. How many distinct factors? 2. What are the x-intercepts? Okay, 0 and 2, good. And then tangent or crossing? Both. This one's going to be tangent, and this one's going to cross, right? Everybody agree?
Yeah.
Because it's an x squared. If the x minus 2 were the quantity that were being squared, that would have been the place where these would have been switched. It would have been tangent behavior at the x-intercept, right? How many turning points is this one going to have? 2. Okay, now let's think about this one. We can already start to get a little bit of a sketch of this. And this is just ironic. This is exactly what we're doing in calculus, just with a lot more bells and whistles at this exact moment. So if we were to sketch this thing, we know we've got an x-intercept there, right? We know we've got an x-intercept there, and we know what the end behavior is, right? We know that the end behavior to the left, as x approaches negative infinity, what's the function going to do? It's got to go down, doesn't it? Because if I were to multiply it out in this column, I'd get f of x equals x cubed plus a bunch of other junk that I don't care about. That's the leading term, right? And it's an odd exponent, right? So I know it's going down there and up there, right? So what does this thing essentially have to do? Doesn't it kind of have to just do something like that? Everybody agree? It's the only way I could draw it, isn't it? I don't get the specifics because it's a sketch, but it can't have any other behavior. How could it be tangential there and cross there and have this end behavior and do anything else? It couldn't, right? Does that make sense? It's kind of like a puzzle. Okay? So then we could fill in the rest from our little sketch here. It's going to have 2 turning points, right? And it's going to have 1 max and 1 min, right? And they're going to be relative. In fact, is this function or any of these functions, tell me right now, going to have any global extrema?
No.
How come? Because it's cute, right? Because of the end behavior, right? So we could never have a fixed peak or valley higher than infinity or negative or lower than negative infinity, right? And that's where the function's going. So we'd have 1 relative, 1 relative. Now what about this one? Last one. How many distinct factors?
3.
How many turning points? Oh, x-intercept, sorry.
-2, 0, and 2.
-2, 0, and 2. How many turning points? Let's go back and look at something on our last one. If you go down to row 4, what are the numbers there? We fill those in. We had 0, we had 0, 2, wasn't it? 1, sorry. 3 and 3, right?
Yeah, the first one's not 0.
Oh, it's 1, you're right, sorry, 1. And the second one's 2, isn't it?
No, that's one.
Oh, that's the one, yeah, you're right, okay. Yeah, you're right. Okay, now what's the order of this polynomial? In other words, what's the highest power?
4.
4, okay. What's the biggest possible number of turning points we have? 3. We could have had less, but we could have never had more than 3, because we looked at every conceivable. this is gonna be the most active polynomial, right, that has 4 distinct factors and 4 x-intercepts. And that only gave us 3, right? Can you think of maybe a generalization we could make about polynomials? So what do you think, if I had a 6-degree polynomial, what's the maximum number of turning points you think I can have? 5, yeah. 1 less than the degree of the polynomial, which makes sense if you think about it, because if these are each going to be x-intercepts at the most active case, then the polynomial can only turn between the x-intercepts, right? Does that make sense? So I'm only going to be able to have the internal intervals between those zeros are going to be my turning points. And so I'm going to only get at the most 1 less than the degree of the polynomial, right? So we can take that knowledge now and carry it into this situation. So what do you think I'm going to get there? Oh, yeah, right here. Let's fill this one out. It's got to be 2. Oh, gosh. You guys must just have fun laughing at me up here. 2, right? Tangent or crossing?
Cross.
Going to be crossing all of them because none of them are multiple roots, right? So they're all going to cross. And how many extreme values? We're going to just get probably what? If I'm getting 2 turning points and I've got to have this opposite end behavior. Oh, we call them locals. Yeah, I always, calculus we call them relative. I should say local. Right? Does that make sense? Okay. What if we, oh man, we just need a little more time. Okay, that'll get you going. There's one other little trick I want to show you tomorrow, and then I'll let you kind of work on the worksheet for the rest of the day tomorrow.